Welcome to another video in the Matrix of Time series. This one is called It's All Relative, and we'll look into some of the relativity theories of Einstein and how it affects space and time. So let's start. So no absolute frame of reference. This falls out of Einstein's theory of relativity. In a previous series we had looked at the case of the observer inside the train, boxcar, and outside, and how this changed what the person saw. And this is pretty important. So it means that when you're looking at events in space and time, it's pretty important to find out where your frame of reference is relative to the event that you're looking at. And here we had a case where the observer was inside the car and would see the same thing that the person inside the car doing the action was, bouncing the ball up and down, and the observer was outside of the boxcar as it went by, and they saw a totally different thing. But there, with Einstein's theory of relativity, there is a way to connect these two mathematically. There is a way to transfer the viewpoint from one frame of reference to the viewpoint in another frame of reference. But what does become pretty clear is that there is no absolute frame of reference, but that whatever you're doing, it's very important that you understand what your frame of reference is relative to the event that you're looking at and how it impacts what you see. And so for us, it's really important that we understand a couple of key features that we're going to explore in this video series. And the first one is our frame of reference as humans. So let's look into that. So our frame of reference in space. So we've talked about this before. We basically have our place on the surface of the Earth. We're spinning around the axis of the planet's moving around the sun, and the sun is moving around the Milky Way galaxy. And our frame of reference is changing in many different ways. The Earth is rotating around the equator about 1,000 miles per hour. We're spinning at 67,000 miles per hour as we rotate around the sun. And our solar system is, moving at 500,000 miles per hour as we rotate around the Milky Way center. So this is some incredible speeds and pretty complex motion. And luckily, all of these motions are constant. And as we learned before, when we have constant motion, we don't feel the motion. And it basically feels to us as if things are still, which is pretty much the way we experience it. And so let's look at how we define our reference frame relative to the surface of the Earth. So now we look here. In this case, we have a human on the surface of the Earth. And if we're going to take our reference frame from here to the solar system or to the cosmos, we're going to do it relative to the center of the Earth. So let's find out how much our position changes from the center of the Earth. Now, the Earth has a radius of about 4,000 miles. So if you fly in an aeroplane, you go 7 miles up into the atmosphere. So if we look at that, we say 7 divided by 4,000 miles. So flying in an aeroplane, your position relative to the center of the Earth changes by 0.818%. How about in the other direction? So in the other direction, it might be when a person goes down a mine shaft or in a submarine. And in this case, in the extreme case, it would be 2.4 miles. And if we divide that by 4,000, we get 0.06%. So for all intents and purposes, our position on the surface of the Earth relative to the center of the Earth is pretty much the same for all people on the surface of the Earth, no matter what activity they're doing. So all humans can be considered to be in the same frame of reference when we're looking at anything that's happening, A, on the surface of the Earth, B, relative to events happening in the solar system, and C, relative to events that are happening out in the cosmos. So now let's look at the frame of reference, and this time in relation to the variable of time. In 1 second, light going 186,000 miles or 670 million miles per hour goes around the circumference of the globe 7 times in 1 second. So let's try to figure out what would be the maximum amount of delay between two humans anywhere on the surface of the Earth, assuming that the communication is a link around the surface of the Earth at the speed of light. So the maximum distance would be if you had two humans exactly at opposite ends of the Earth. In this case, you would have a delay of about 67 milliseconds. As we'll learn later in this series, conscious human response time is on the order of about 100 milliseconds. And to verbalize that conscious interaction is on the order of 500 milliseconds. So for all intents and purposes, any place on the surface of the planet is experienced as instantaneous by all humans for communications at the speed of light. Now, what if we take this frame of reference in time relative to the cosmos? We'll find out that longer delays break down the now. Let's start with the first one. We have a human on Earth and we have a being on the moon. And the delay of communication between the human and the being on the moon would be 1.34 seconds. So a communication back and forth, the human would then find that there could be a delay of up to 2.6, 2.7 seconds for a response, which would be pretty annoying, but still doable. Now let's take another aspect. Let's say that there's a being on the sun, ignoring all of the heat effects. This is just a thought experiment. Now we find that the delay to the sun would be 500 seconds, or about 8.3 minutes. So this is far more significant. So trying to communicate even at the speed of light with a being on the sun, you communicate it takes 8.3 minutes out, 8.3 minutes back. That's quite a long time. And the being on the sun would always see the Earth 8.3 minutes in the past. The now that we experiencing would be 8.3 minutes in their future. Now let's take it even further. Let's go to the nearest star relative to our solar system, and this would be Alpha Centauri. And that closest star is 4.4 light years away. So the being in Alpha Centauri would see Earth as it was 4.4 years ago in the past. And our now, like you watching this video, would arrive to them 4.4 years in their future. And so you can see that that's just with the closest star. You can see that the whole concept of now as a reference frame starts to break down very rapidly once we start to move away from the surface of the Earth. We've basically shown that the concept of an ever-present now to beings in our solar system or in the cosmos is not possible. But can we actually stop time? And what would that look like? So we know, based on the previous example, that every moment of now is moving away from the surface of the Earth at the speed of light. So if you could move at the speed of light, you could actually keep up with that moment of now. And if you stayed at the speed of light, you would be forever immersed in that existing moment of now, and you would experience time as having stopped. Since everything that you see that is part of that now would show that the universe never appears to change. Now, if you could move faster than the speed of light, you could immerse yourself in information that was represented a few seconds before, or many hours ago, or even hundreds of years ago. So you could look into the past because you would be able to overtake that moment that happened years ago that's still moving out into the universe, and then you could immerse yourself in that exact moment as it happened a few seconds ago, a few hours ago, or even a few hundred years ago. Now, Einstein's relativity does not outlaw faster-than-light motion, but faster-than-light motion does lead to time travel, so signals could go back into the past and potentially change an event that happened. So physics put a speed limit on motion, the speed of light, and this is enforced by a COP, which stands for Causal Ordering Postulate. This COP prevents processes that lead to time travel. But we discussed it here just so that you understand the possibilities of what happens when you move faster than the speed of light. Let's look into a clock that is based on using photons as a mechanism to mark the passage of time. And this clock, in the left-hand side, you can see two mirrors, and you see a photon of light that bounces between these two mirrors. And each bounce of the photon represents a unit of time. In this example, let's assume that the photons of light move slowly enough that we can see them bounce between the mirrors, sort of like a massless ball would. This representation is a pretty good way to show how atomic clocks are working on GPS satellites. And these photons from atoms bounce between these mirrors, as an analogy, 10.23 million times a second to create the accuracy that is needed to generate the GPS positional accuracy. Remember that at the speed of light there is 186,000 miles or 300 million meters for each second of time. So to measure just a few feet or meters, you need to measure very small amounts of time. So speeding things up slows down time. So we're going to look at an example of two astronauts in Rocket A and another one in Rocket B. And you probably see something familiar. It looks like a ball bouncing up and down, but actually this is the photon clock. So we're going to represent the two white circles with the black rings. That's going to be the photon bouncing up and down. I'm going to ignore the mirrors for now. And we see the same thing. In Rocket A, we've got Astronaut A. They have an inside perspective. And basically the distance between the two mirrors is defined as shown here, where it's a straight line between the photon bouncing off the top mirror and the bottom mirror. But when they look at Astronaut B in Rocket B, who has the identical photon clock, they see the photon, moves sideways as the rocket passes them. And so the distance between the upper mirror and the bottom mirror increases. And so from the perspective of Astronaut A, Astronaut B's clock is running slower because from their perspective, the photon has to travel a larger distance between the mirrors, effectively making each unit of time longer and slowing things down. So now we have two astronauts checking each other. You've got Astronaut A who looks at their clock and says, everything's running fine, sees Astronaut B and Rocket B flying by, looks at it and says, oh, their clock is running slower, and communicates this and says, hey, Astronaut B, your clock is running slower. Astronaut B looks at their clock in the bottom right-hand corner, says, nope, my clock is running fine, looks outside, looks at Rocket A, and communicates back to Astronaut A and says, actually, it's your clock that is running slower. So you can see this can keep going in a circular reference because it's all a matter of frame of reference. And as we asked before, who is right? Well, they're both right. And that's the interesting part about this whole aspect of the special theory of relativity. So Einstein's theory defines how these two astronauts resolved this. And he came up with this equation, which he called the interval in space-time. And basically there are two components. There's an interval in time and an interval in space. you take the square root of the interval in time squared minus the interval of space squared. But as we remember, we first have to have everything in distance, and we know how to convert time to distance. We do this by using speed, in this case, c, the speed of light. So the interval in space becomes the square root of c squared times the interval of time squared minus the interval of space squared. And now the units are all in distance. So let's look at rocket A, where the person is inside the rocket, and the interval in time is the time it takes the photon to bounce between the two mirrors. And the interval in space is the difference between the movement of the clock and the movement of the observer. Since they're both on the rocket, the interval in space is 0. So when we do the calculations, we take the square root of the interval in time, which in this case is 6 feet squared, minus the interval in space, which is 0, and we get an answer of 6 feet. Now, in the other rocket, because it's moving relative to the first rocket, and remember, in these examples, these two rockets cannot be moving at the same speed. If they're moving at the same speed, they'll both see each other's clocks ticking off at exactly the same time. It's that they are moving relative to each other at different speeds, and the bigger the difference in speed, the greater will be the slowing down of time. So in this case, as we can see from that black arrow, there's a longer distance that the photon has to travel between the mirrors. And in this case, when we do the calculation, we find out it actually lands up being 10 feet. And the interval in space, meaning the difference between the observer that's looking at the clock from the other rocket and the rocket that's moving past him in that period of time, was 8 feet. So when you take the square root of 10 squared minus 8 squared, you land up with 6 feet. So both of these astronauts can agree that if they convert their experience of their clock time into the interval of space-time, they get exactly the same answer. And this was a very ingenious outcome of Einstein's special theory of relativity, that whatever frame of reference you're in, you're going to see a unique viewpoint of the universe, but through these equations, through math, you can translate what you're experiencing relative to what the other person is experiencing. And so these conversions can be done, and you can see how this has been done in this example. One of the other effects of Einstein's relativity is that it breaks down the moment of now through motion, so that people in motion relative to each other cannot agree on a simultaneous moment. So let's look at this. So here we have an example. Again, we're using the train. I'm using an example of a lightning bolt striking both the front and back of the train and the track at the same time. This example was given in Space-Time Physics, a book by Wheeler. And at the time when Einstein wrote this relativity theory, trains were the most popular form of transportation. But here we have the lightning striking, and we have an observer inside the train, or we'll call him a person inside the train, and the light from the two lightning bolts that struck the front and the back at exactly the same time travel towards that person, and it sees them both reach him both at the same time. Now there's an observer standing outside watching this, sees the lightning bolt hit the tracks, and also the light from those two lightning bolts reaches him at exactly the same time. So these two people will agree that both bolts reach them at exactly the same time. Now what happens when the train starts to move? Let's say it moves at a pretty significant speed so that it impacts the speed at which light reaches you. Now the person inside, the way that they'll experience this is that the light photons that came from the lightning strike in front of the caboose, they are moving towards that, so the path that these photons coming from the front have to travel will be less, and the path from the back will be longer. So the person inside the caboose will say that I saw the lightning strike the front of the caboose before it struck the back of the caboose. The person outside still sees exactly the same thing because they are not in motion relative to where those two lightning bolts struck the track. So what's going to happen is that these two people are going to disagree about the exact moment of now. The person outside saying, nope, both those lightning bolts reached me at the same time. And the person inside saying, nope, the one in front definitely reached me before the one in the back. And what this is going to do, it's going to impact how you measure distance. And the effect of this is that the observer in the train is going to measure the distance the same, but the observer outside is going to measure the caboose as shortening in the direction of travel. So let's look into that a little bit more. So now we're going to look at Lorentz contraction. And what Lorentz contraction is that space will compress in the direction of motion. Now, this is not really intuitive, so be patient with yourself. If we go through this and you don't get it the first time, try to go back to the previous slide about the disagreement of simultaneous moments and then come back to this a few times. So the example that I'm going to put here is how the frame of reference changes how you measure distance. And I'm going to use two amazing tennis players, and they can hit the ball at 95% the speed of light, so about 637 million miles per hour. Kind of makes the professional players who seem to do it just over 100 miles an hour look pretty weak. So that's why I say these guys are pretty amazing. Now it has to be this fast because these effects from relativity really only start to be noticeable when you get closer to the speed of light. You know, most of our lives are spent at tiny, tiny fractions of the speed of light. Even if you are in the space shuttle going 17,500 miles per hour, that's a small fraction of the 670 million miles per hour that the speed of light goes. So that's why these examples we use speeds that fast. So anyway, we start off that we have a tennis player on the left-hand side, and this person serves the tennis ball. The tennis ball is in motion, and the other tennis player on the other side is waiting to receive the ball to hit it back. And we have an observer. The observers in this example are going to be in yellow. And they're standing on the earth, signified by this brown line, and the tennis players are on the tennis court, signified by this green line. And everybody is spinning along with the earth. And there's pretty fair agreement because relative to the yellow observer, the two tennis players are moving in the same frame of reference as they are. So there's no problem. So when the yellow observer goes to measure the distance between the two tennis players, they measure the distance just shown on the bottom. Now, let's switch the frame of reference. So now in the frame of reference, we're going to put the observer as a tiny little observer who's traveling along on the tennis ball. So for them, everything, their frame of reference is still. It's like them, like if this person was traveling in an airplane. They can move around, everything is still. They look outside. The two tennis players are zipping by them. The observer outside standing is zipping by them. So they're still, everything else is moving by. And what they notice is when they're standing still, the other tennis player is about to hit the ball is traveling towards them, and they see this distance as shorter. So you can imagine, because this tennis player is coming towards them, they're not going to measure the distance the same. So when we look down at the bottom, we saw that the original observer had this one ruler and measured. Now the observer is on the tennis ball, and they have a shortened version of the distance between the tennis players. So here you can see that your frame of reference changes how you see things. And again, we have the same issue as we did with the time dilation in the two rockets, is that they cannot agree on time. So we've shown how motion changes time by slowing it down. Motion changes space by compressing it. But it also does another thing, and that I'm not going to go into details, but that motion also changes mass. So what we notice is that space, time, and mass are not absolute. What is absolute are the laws of physics. So we've basically, what Einstein's theory has done is wiped out just about everything that we thought was sacrosanct, and that is that we can rely on space, we can rely on time, and we can rely on mass to help us give structure to space and time. And he's saying, nope, can't do it, that these three properties of space, time, and matter are not absolute and change depending on your frame of reference. So, GPS, an example of how relativity affects us. So, let's look at a situation where we have the average earthbound cyborg, that is a human with an attached smartphone. And when they use their smart apps when they use their GPS apps in their smartphone, it has a resolution of about 4.9 meters or about 16 feet. To get that accuracy, a number of significant effects have to be accounted for, two of which are related to these theories of relativity of Einstein. Let's look at the first one. One of the errors that the GPS has to account for, that is from the special theory of relativity, is the time dilation effect. This effect accounts for 7 microseconds of error in positional accuracy. Now we already know we can convert the 7 microseconds into distance, and when we do that, we find that just this one error creates a positional error of 2 kilometers or 1.3 miles. That's a 438x loss in positional accuracy. Now the second error that the GPS has to account for is from the general theory of relativity and is related to the fact that objects with large amounts of mass, like planet Earth, distort space and time. This effect accounts for 45.9 microseconds of error in positional accuracy. Now when we convert this into position, we find that this error is comparable to 13.8 kilometers or 8.6 miles, a 2,800 times loss in positional accuracy. And in fact, what this shows us, if we don't use relativity, the GPS becomes pretty well useless, especially in cities. So let's dig into these two effects of relativity into the GPS example a little bit more. So in this diagram, we have the earthbound cyborg, whose average speed spinning around the surface of the Earth is about 500 miles per hour. The average speed of the satellite is about 9,000 miles per hour, and the mass of the Earth is about 6 times 10 to the 24 kilograms. So let's use these variables to understand how this affects the error in the GPS positional accuracy. So the first effect we'll look at is the time dilation effect calculated from the special theory of relativity. And that's due to the difference in the speeds of the clock in the satellite as compared to the clock in your smartphone. And this creates a 7 microsecond per day delay between the two, so time slows down. The second effect, called the gravitational time dilation, or the gravitational frequency shift, is an effect that's calculated from the general theory of relativity. And that says that the closer a clock or any process is to a large gravity field, like the mass of the Earth, the slower the passage of time. There is an increase of 45.9 microseconds per day between the atomic clock and your smartphone clock, so time speeds up. So you have two effects from relativity. One that accounts for time slowing down, and the second one for time speeding up. The total error of these two relativistic effects is 38 microseconds. This translates to 11.2 kilometers, or a 7-mile positional error. So you could see that if these two effects from relativity were not accounted for, that we really have to pay attention of frame of reference and to motion, that it would make the GPS app useless in any town or city. So I hope this example gives you a good appreciation that your frame of reference in this universe really matters, and that motion relative to your frame of reference changes what you see, and this has to be accounted for. Takeaway messages. The universe is in constant motion. Motion affects time and space, as well as mass. Gravity affects time and space. In this objective world, we have to be aware of how the event or object we are viewing or measuring is moving relative to us. And of course, we have to pay attention to how our motion is relative to the event. There is no absolute frame of reference. It is all relative. The laws of physics are absolute in all frames of reference. Now, in the next video, we'll see how the state of the split personality of matter is dependent on whether there is someone watching it or not. Quantum theory gives us a whole new view on how matter behaves at the smallest levels, and experiments in quantum physics with atomic particles will challenge our understanding of time. I hope you join me. If you'd like to watch more of the Matrix of Time videos, please hit the subscribe button and you'll be notified of new presentations. You can also visit my webpage at www.multidimensionaltime.com, and in there you will see a reference to a book I've written that you might be interested in. Also, I have a page with technical papers. There's an intro paper, and there is a paper called Three-Dimensional Time and Consciousness in the technical section that'd be of interest to people with and without a technical background. And then the rest of the papers require an engineering or science background because they get quite technical. So again, please hit subscribe and join me in not only future videos of this Matrix of Time. There will also be other series related to space and time that I'll be doing in the future, and you'll at least be notified of those as well. Okay, thank you very much.